All right, so our second talk is by Shivam Pandey, and he'll be telling us about understanding matter distribution from the SCFI.
All right, thanks a lot, everyone. Thank you to the organizers for this very engaging conference. So branching off from yesterday's discussion session, I'll be talking about how to understand matter distribution with the SZ effect. Because yesterday, one of the worry was for example, like understanding the S8 tension, we have to worry about baryons as you push to small scales. So it'll be good to have some complementary constraints on how much baryonic feedback there is in the universe. Okay, so very high energy processes that go inside the galaxies that we have very poor understanding of, for example, the active galactic nuclei or the supernovae feedback that they impact the gas density as well as the dark matter profile. So for example, in here, one of the simulation, if you see the no feedback column for gas density, and as soon as you start the feedback, you can see there is more gas in the void region or the empty region. And this particular movement of gas also have a effect on dark matter distribution. So overall, the total matter distribution does get impacted. So to understand this, we just do a very simple statistical analysis, for example, the matter power suppression. So basically what we will be interested in is what the total matter power suppression is in a hydrodynamical simulation relative to the dark matter simulation. But note that the initial conditions are paired. So the so-called sample variance will cancel out. So effectively, you're seeing like if you just turn on the hydrodynamical prescription, keeping the initial conditions same, how much the total matter power changes. And this particular quantity is fairly poorly constrained and currently comprises one of the leading theoretical systematics in the cosmological analysis, particularly with peak lensing. Just to get a gauge of it. So for example, in here is similar quantity instead of delta P over P, it's just P hydro over P dark matter, so centered around 1. And all the different curves that you see are the estimate of this from various different hydrodynamical simulations. So these different simulations have different prescription of what the baryonic feedback is. And you can see there is like order 20 to 40% scatters as soon as you go to K around 1 or a little bit above 1. Or even currently, the weak lensing surveys are sensitive to 0.1 to 1, but even here you can see there is more than a 10% scatter, and we want to get 2% level cosmology. So it'll be good to get a handle of this from some other probes. So for example, like can we understand this or like get a handle of this, for example, from some KSZ effects? So a few years back, there was this very interesting paper that tried seeing a correlation between this power suppression relative to what the baryon fraction is. So baryon fraction in halos for around mass 10 to the power 14. So this thing is measuring what the number of baryons is relative to total matter in halos 10 to the power 14 and trying to see what the power suppression is at some scale K of 0.5. And what they see is doesn't matter what kind of simulation they use. So in here they only use like 6 or 8, but there's a fairly tight scatter in what the power suppression is and what the baryon fraction is. And you can kind of intuitively understand this. At this regime where there is fairly less baryonic feedback, the baryon fraction will be very close to cosmic baryon fraction, so omega b over omega m. And hence the power suppression will be small. Whereas at this end where there will be a lot of feedback, there will be less of baryons inside the halos because the baryons will be pushed out because of powerful AGNs, and hence there will be more power suppression. But so it'll be good to understand how this changes if we change or like analyze more of the hydrodynamical simulations, as well as if we go to different scales, different halo masses, etc. But the main thing is that the baryon fraction is fairly hard to measure. So you can use something like X-rays going or targeting like low redshift, high mass halos, or you can do something like KSZ effect that Gil just talked about. But we already have significantly higher signal to noise in the thermal SZ effect. So I'll just borrow the introduction from Gil and just say that in whatever he showed, if you just replace the bulk velocity with the thermal velocity of electrons, you get something called as thermal SZ effect. And this thermal SZ effect is sensitive to the energetics. So in addition to the gas content, it's also sensitive to what the temperature of the gases, and but that will be correlated with how much baryonic feedback there is. So can we get some handle on on the baryonic feedback, as well as how it affects the total matter distribution by just analyzing thermal SZ effect. Okay, so the motivating question of the talk would be, does the relationship that I just showed from Vandalen et al. Generalize to other feedback model? How does it change with halo mass and scales? But more importantly, is there a tight relationship in power suppression and thermal SZ signals of halos? And if there is, can we already use it to get some constraints on delta P over P with the existing data? So to that end, we will be using these camel simulations. So the camel simulations are like 25 megaparsecs POC, but they change a lot of different hydrodynamic prescriptions and the amount of baryonic feedback. And you have access to quantities like what the gas pressure is, what the electron density is, what the dark matter density is, and lots of other derivative products. So you can see that the gas pressure changes substantially as you go from no feedback, you change the supernovae feedback, you change the AGN feedback, or like relative to some fiducial model. And that similarly for electron density and total dark matter distribution. So in the set that we will be analyzing, like the simulation suite has 3 different prescriptions, so TNG, SIMBA, and ASTRID. And for each of these 3 that use completely independent code, they change 2 parameters that control the supernovae feedback, 2 parameters that control the AGN feedback for each of the 3 simulations. But one thing to note is that, for example, if you take any of the particular parameter, their physical meaning is kind of different. So if you just take, for example, the AGN2 parameter, which turns out to be an important parameter in the study, in TNG and SIMBA and ASTRID, it overall controls different physical quantity. And in the end, what it does is like it has a non-intuitively different impact on the power suppression. So basically, all this to say is that instead of just, for example, like trying to understand how the power suppression changes as a function of these parameters, it will be good to see the correlation in the power suppression and something physical, for example, the SZ effect, which has to be shared, or like which has to be a physical thing that's correctly modeled by all of the hydrodynamical simulations. So basically, just to mention that the simulation set is for each of the 3 codes, the TNG, SIMBA, and ASTRID, they will have 1,000 simulation in the full Latin hypercube grid, sampling the cosmology, the four baryonic physics parameter, as well as varying random C. But they also provide, if you just vary one parameter at a time, or the cosmic variance set, which only varies the initial conditions, keeping all the cosmological and baryonic parameter fixed. So effectively, they have like 3,000 simulations for each hydrodynamical and the dark matter only. So effectively, order 6,000 simulations that we analyze in this study. And if you take interested in how the power suppression looks like for the camel sims, so in here, what you see is the power suppression as a function of scale for TNG, SIMBA, and ASTRID. So the 3 different colored ones are the cosmic variance set. So it's literally just changing the initial conditions. But again, as I said, the actual sample variance, the cosmic variance error cancels out. So whatever error bar that you see in the 3 are this actual stochastic error due to just changing the initial conditions. But another thing to note is the light blue error bar. So what that thing shows is the error bar in the power suppression from the Latin hypercube set. So remember, Latin hypercube set was varying all the baryonic parameters as well as initial conditions. So it is just to say that the actual variation when you vary all the physical parameters is significantly larger than if you just vary the cosmic variance set. So this will be important as I will show the results. Okay, so we can just now directly go and see what the scatter looks like. So in here, this was the Vandalen et al. Plot that you saw before. In here is a reconstruction of that at slightly different K value and slightly different mass value, as will be relevant for the little bit smaller box size of camels. But you can see that if you just look at its scatter with relative to FP, so similar parameter as here, it's a pretty similar scatter, or like pretty similar relation, but with a little bit larger scatter that is a little bit due to going to smaller halo masses and a little bit smaller scales. But what's more interesting is if you make that same scatter plot for the SZ signal. So this is, instead of counting the number of baryons, you count the thermal SZ signal within some radius, but you divide out the self-similar scaling, which is like analogous to the baryon fraction. And you see there is a fairly similar relation as well as fairly similar scatter if you make the plot with the thermal SD. And each of the points are color coded by the amplitude of the AGN parameter, the parameter that I mentioned before. So this is also interesting to see that as you increase the AGN feedback, you start to see more or like less SD signal and less FP, like because the more of the baryons are pushed out and more power suppression. But you can try to see how this thing, so sorry, this is a busy plot, but I think it's still interesting to see that if you make the similar thing for all the 3 different hydrodynamical prescriptions, so TNG, SIMBA, and ASTRID for FP, you can see that, for example, if you focus still on the higher mass halos, the scatter and the relation changes substantially. Like SIMBA has significantly larger feedback for the same given AGN value relative to TNG and ASTRID. But what's interesting is that for Y500 or like the DSD signals, like very similar relation exists. And you can try to push to smaller halo masses as well. So 5, 10 to the power 12 and 13. So in here, the error bar or the scatter gets larger. But again, the same thing remains true that for the KSD signal or baryon fraction and thermal SD signal show fairly similar relation and scatter. But so one of the motivating question that I posed is how does this relation look like for different scales? So in here is this delta P over P as a function of FP, but similar things remains true if I do thermal SD. You can see that as you go to smaller scales, the relation changes substantially. So it'll be good to understand why exactly it has this kind of shape and can we understand this thing a little bit physically. So let's consider 3 different scales. So the halo radius, which is RH, the distance to which the gas is ejected due to any feedback process, so say R ejected, and the scales at which we actually measure the power suppression, but we will kind of do a hand wave and say the scale is equal to 2 pi over K. So let's understand for the case where the halo radius is smaller than the scale at which we are measuring the power suppression. So in here, if you're particularly in this regime where the feedback is a little bit small, so if any feedback process happens, it will eject the gas. So R ejected will be here, but it will still be smaller than 2 pi over K. So the gas will be ejected, so FP will change, but it won't change the power because the total mass inside the radius remains the same. So it will follow this kind of horizontal thing. However, as soon as it gets really large feedback, so R ejected will be large beyond the 2 pi over K, so it will change the power. So this is what you were seeing in here, that when you're interested in larger scales where 2 pi over K is larger, it follows flat and then drops off. Whereas if you go to the other regime where your R halo is larger and 2 pi over K is smaller, so it's like other large halo or small scales, any feedback that happens, it will eject the gas, so it will change the FP as well as change the power. So this is exactly what you're seeing in here. As you push to small scales, the relation becomes fairly linear. So in the paper, we give some approximate analytical form for this. Okay, so now I think it's time to take this thing and go to and see if we can actually make a emulator out of it. So we take all the points that you saw in here and try to train a random forest regressor that trains the relation between any of the input quantity and the output quantity, that is delta P over P. So we train on all the 3 simulations, and in here what's plotted is the error in the recovered delta P over P relative to the cosmic variance error, because that is more or less as best as you can do, and the plotted is in sigma. So plus minus 1 sigma gray band is as best as you can do, and what you can see is that if you give the TSD signal, which is by 500 over YSS, you recover fairly similar results on delta P over P as a function of scale. So it seems like this random forest regressor is a pretty good model. Like given any of the SD signal, it can give us a handle on delta P over P. So it'll be good to see if we can connect it with data. So one of the data set that we use is thermal SD cross weak lensing, and both of them you can say that it will probe very similar large scale structure, because it's the galaxies or like the matter distribution that lenses the background galaxies is correlated with the electron cloud that does the thermal SD, causes the thermal SD effect. So we take the measurements from DS and ACT correlation, we break it down into a halo model, so 1 halo, 2 halo, and some systematic. So, but effectively, it's a function of pressure profile, function of the dark matter profile, and function of cosmology. And we vary these parameters, fixing the cosmology to Planck and DES. And effectively, with the constraints on the pressure profile parameter, what you can do is translate it to what the thermal SC signal looks like for some halo masses. And remember, this is exactly what was the input in our random forest regressor model. But what's important is this thing folds in all the measurement and modeling uncertainties. So what you recover in here is the pressure profile with the proper error bars. We can also take some future data. So in here, instead of weak lensing cross shear, you can be, which is sensitive to wider halo masses, you can try to go to some particular halo mass range. So you can take some halo cross SD signal directly. So in here, we try to take the DESI group, mock DESI group catalog, mock S4 or SO thermal SD map, and you can try to see what pressure profile you can expect to get for some halo mass range and some particular redshift. And this thing is fairly tight. But again, like I would like to emphasize that this thing folds into a bunch of expected modeling and observational uncertainties. So, okay, taking these pressure profile expectations or the constraints and trying to infer what the Y500 is, and we take this particular model and predict what the power suppression looks like. So here is our results. So in here in black, error bars is the result on the power suppression as a function of scale from the DS cross ACT data, so weak lensing cross SC data. And we compare that to the current existing constraints from Chen et al., which analyze the small scale weak lensing signal, and Schneider et al., which in addition also analyze the X-ray and thermal SC data. But what's even more cool is if you look at the blue error bars, which is the DESI cross S4, the 4 cross, that seems like it will be able to tighten the error bars significantly. And this is mostly related to getting very tight constraints on the pressure profiles with the halo cross as the signal. And once you have this kind of very tight error bar, you will be able to more or less demarcate between various different hydrodynamical prescriptions. As you can see, the OWLs, Bahamas, or TNG is giving us very different delta P over P. And with this kind of tight error bars, you're able to say, okay, which hydrodynamical simulation is close to reality. But in addition, it gives you a prior to confidently analyze the small scale weak lensing signal. So basically, in summary, I think like we did find there is a tight relationship between delta P over P as a function of thermal as the signal. And it more or less does generalize to different feedback model. And we can come up with some sort of simple analytical scheme to explain how this changes with different halo masses in K. And in the paper, we also see how does it generalize to bispectral suppression, finding that it does. However, the box sizes of camels are too small to actually do this thing with data, which is not the case for power suppression. So we can't say something with the current data. But yeah, I would encourage people to look at the paper for more details. That's it. Thank you.
Questions?
It went a bit fast, so probably you already answered this. So the differences between TNG, Astrid, and Simba. Right? So you have used these three now because Camels has used these three. But do you worry that the fact that there are large differences here means that your training set may actually not be complete? As in, if I come up with a slightly different prescription for feedback and did an extension to Camels, that might get substantially different answers.
I mean, that definitely is true. Although I would say that for each of the prescription, they have like 1,000 different realizations. So there will be some degeneracy between, you know, for example, taking different feedback parameter for TNG versus like having a completely independent hydrodynamic prescription. So I think like we are capturing a bunch of differences, like because in here, this is like 6,000 different realizations with very different feedback processes, right? So there'll be some degeneracy when having a completely independent code. But I mean, that worry is there that if you have the fourth one, it could be that it doesn't fully generalize.
Priyanka, and then Surhud.
Hi, nice talk. Going to the last plot you showed. Yeah, using these results, this across ACT results, can you say that TNG is wrong, the TNG 300?
I mean, it's like 1.5 or 2 sigma. So at that level, probably, but I think like from few different correlations, that has been the case that the inference on feedback always seems stronger than what TNG 300 says. So, but I don't think like not at 4 or 5 sigma. So, but hopefully with the future forecast, you will be able to say that.
Okay, let's say with DESI S4, you'll be very definite.
Yeah, if it is wrong or not. Yeah.
So my question regarding the variation that was done in the parameter choices for the simulation. So what kind of priors are taken in order to figure out like how much to vary each of these parameters? Are there certain types of observables that they try to match and any sort of degeneracies that they try to account for? Or
no, it's completely free and fairly wide prior. Like cosmology goes from like 0.1 to 0.6 something, and but baronic feedback parameter also are like very wide and uniformly sampled.
So there may be some other observables that
will rule out. Yeah, exactly. Yeah, that's for sure. Like we do find, I think there is some paper by Camels that says that a bunch of them don't, for example, reproduce the star formation rate constraints, etc.
Exactly. So that's what.
Well, that's true. But I mean, for training these kind of models, it's usually better to have, for example, like training machine learning models, better to have a uniform sample and then let data figure out what does it prefer.
So the question is always what kind of data are you using, right? Whether there are other better probes which will rule out any of these possibilities.
For sure, yeah.
Right now your error bars are quite large.
Yeah.
Maybe if you add in some other
Agree.
sort of data.
Yeah. So having like multi-probe analysis is definitely the way to go. Yeah.
It's sort of related to the questions that was asked already. So since you've been thinking about these hydrodynamic simulations, you showed that, going forward, you'll get really tight constraints and maybe it will fall on one of the simulations. But as you said, like there's no physical understanding about why that particular simulation is getting this particular observable correct. So how do you then, like, what do you do with that information?
No, exactly. So I guess like that will be crucial, that even if you can say which simulation is correct, then you should go to that simulation and try to validate that it reproduces all the other things also.
Yeah, you need to check every observable one by one and make sure that it's right.
But it's much better, right? Like if you can figure out few of the simulations, then instead of searching the whole space, then you can just focus on the observables from those simulations. So, but I agree. Yeah, you would need to do that.
Shadab.
So when you looked at as a function of K scale, you give this physical description about at large K, you're going to always have seen feedback effect. But we have seen several aerodynamical simulation where the power at large K start to go up once you start hitting the stellar density, which is probably already at K of 10. But none of your
scales. You mean small scales?
Right, small scale, large K.
Okay.
And so you should see a delta P of positive rather than a negative, but none of your simulation shows that.
No, they do. I think like we cut off at K of 10, right? Yeah, we cut off at K of 10. I think like, yeah, if you take these boxes and go to K of 20 or 30, bunch of them do go up.
Okay, so it's even at higher K than.
Yeah. So I mean, we do cut off because I mean at K of 10, I think even n-body simulations don't agree as well. So because we wanted to do inferences with data, we only analyze K of 10.
I see. But when you look at this dependence as a function of F baryon, then it will start going up. But you haven't looked at that.
Yeah, so I think like so in the physical model, I think you would have to, for example, account for some sort of cooling effects, etc. So yeah, I mean the model is fairly simplistic, but I agree. Like yeah.
Thanks.
So was there a last question? Okay, yeah.
Do you worry about non-thermal pressure support, either like bulk velocities or cosmic rays that might not be captured in these hydrosims?
I mean, this thing is actually trained on the total pressure. So I think it accounts for it accounts for the non-thermal support as well in the simulations as well. But if there are some other sources that are not already in the simulations, probably not.
But the observable is just the pressure, right? Yes.
It's not just the thermal part of the pressure, it's the total pressure. So because on the simulations, we measure the total pressure, and on the data side also, we measure the total pressure. Like it's only a worry if you're trying to do some sort of halo model inference, right, where you presume some hydrostatic equilibrium and just get the thermal part. But from the both simulations and data, we are measuring the total pressure. So I think in that sense, it should have that component.
We'll talk later.
Okay, yeah.
Let's thank Shivam again.